Hi, everyone. Welcome to Research on the Road. We are talking about dimorphism today, which we'll get into the definition of it and exactly what it means. But specifically, we'll be talking about sexual dimorphism, which is just differences in genders. And so we'll have I have a special guest here, Darwin. He's not showing us any dimorphism, though. He's just here for eye candy. So we'll get to the exciting uh, real life interpretation of dimorphism at the end. So to start off, so dimorphism really is just differences. And so when we say dimorphism, it means two forms of something. So having two distinct forms, and that's di is two and morph is form or shape. So when we're talking about sexual dimorphism, we're talking about the different genders, so the male and the female of the same species actually look different. And that doesn't mean that they're strikingly different. It doesn't mean that they look like different species, but any difference between the way that they are is an example of dimorphism, and we can measure that and we can compare that. So everything that selection favors things that help animals to reproduce better or more. So when we're talking about gender dimorphism, it's typically that there's a preference. So if females like the males that have one form of a trait, then that male is going to be better at having offspring, and those offspring are more likely to inherit that preferred trait. So it spreads through the population because it's selected for. So other influences besides specific choice by males or females is predation. So if you've got a lot of flashy colors and uh, you're more visible to predators, you're probably going to have less of a chance to reproduce. You're not going to have a good chance to have offspring if you're going to get picked off by a predator because you're too colorful and too vibrant and you attract attention. And at the same time, even if you do get offspring, if they have those same traits, they are less likely to survive. So those things that are reduce the viability and the fitness of that organism are more likely to be reduced as generations go by. And another is it's not just that the female prefers a trait, it could be that the males are actively fighting to win the female. So you think of Bighorn sheep, they have those large horns on their head because they use them to fight against each other and to win the females. So those who have larger, thicker skulls and stronger horns and are more likely to win those contests are more likely to have babies, and those babies are more likely to be stronger. So here's some of the obvious examples. Of course, our male lions have a big mane, and they are very obviously different from the female lions. Orangutans, it's less of a obvious difference. I mean, they look similar, but the biggest, largest males are the ones who tend to win the females, and they look even more different from the females. They have those big heads, those big faces, and they are just big-bodied animals. Overall, they are much larger than the females. Mandrills are also pretty different. They are more colorful, the males. Not only that, they're also larger. So they are attracting females at the same time as they are displaying aggression to other males. Elephant seals are much the same. We have the big bull male who is considered the beach master, and he pretty much rules over all sorry bud all of the mating on the beach. Most of the females will end up mating with him, and most of their offspring will be his offspring because he is the biggest and he is the strongest, and he chases away the other males, and he can actually fight those other males and keep them from getting into his territory. Birds, there's a lot of examples of dimorphism in birds. So here's a bird of paradise. That dark void in the middle is actually the male, displaying to the female that's standing in front of him. So they don't even look like the same species. They don't even look like the same animal. But that male has puffed out all his feathers, and he is doing a mating dance with female in front of him. Peacocks are one that are an example within themselves. I mean, that has become the quintessential example of sexual dimorphism. The tail feathers that you think of in peacocks are only in the males. On the right, we have the females, and those would be considered peahens. So even like when you are referring to a peacock, you are specifically referring to that beautiful male, and he only has those striking feathers because he's trying to attract the females. And it's actually kind of a hindrance to him as an individual because he is less able to fly, he's less able to run away from predators, but the ladies like it, and that overrules it. So he can survive long enough that he can have offspring with the females and pass that trait on to the next generation. Mandarin ducks, that's a pretty big, obvious difference. The males are flashy and pretty to attract the females. The Eclectus parrot here, so these are actually a male and a female in the same image. So the males are the bright green emerald plumage, and the females are typically red. They have some blue and purple on them, but they're a complete different color. They're not a different species. They are the same species of bird, but the males and the females are completely different colors. Now going into reptiles and lizards specifically, our big male iguanas have that dewlap on the neck, and they're using that to signal to each other to show aggression to other males, but also to attract the females. And they are typically larger and heavier and have that dewlap that they can extend and puff out. Lava lizards, during the mating season, the males are bright red, and that again is kind of a hindrance to them because lava lizards are very well suited to the lava rock that they live on, and their purpose in that camouflage patterning is to blend in. So for the males to become so apparent and so distinct and separate from the landscape that they're living on is potentially hazardous to them in terms of attracting predators, but it's something that the females are also attracted by, and it better improves their chances to mate. These guys are interesting. Ecuadorian horned anoles. The males have that very long proboscis, that extension on its nose. And then in fish even, the male anglerfish is tiny compared to the female anglerfish. And that is pretty much a result of their habitat that they live in. If you're in a tiny area in the dark ocean and your chances of coming across a female are very slim, the moment a male comes across a female, he's going to latch on and he just stays there for the rest of his life. That is now his partner, whether she likes it or not. Guppies tend to be flashier in the males. the Asian sheepshead wrasse. So this is another one. That large bulge on the top of its head is the male, and that is both to display and attract the females, but also to uh, actually fight and have contests with other males. So they have aggressive displays, and they butt heads with each other, and they come at each other to win uh, the females over their rivals. The paleontological dimorphism record.
All right, so yeah, I'm going to talk about sexual dimorphism that we see in the fossil record. And to be honest with you, it's not that much. Because when we're looking for sexual dimorphism, we quickly run into the limitations of the fossil record. Let me turn on my laser pointer here. So the fossil record is notoriously incomplete. Some have theorized that less than 1% of organisms actually get fossilized. And so that means over 99% of every organism and species that has ever lived, we will never know about because they didn't get fossilized. So not only do we not have most individuals, we don't even have most species that ever lived. We won't know about most of the animals or organisms to ever live, which it's frustrating, but especially in this case. And because becoming a fossil is such a rare chance occurrence, we usually have a very small sample size of different species. So we don't have very many individuals of species that gets fossilized, especially for vertebrates, things with the backbones. And that's everything from fish, amphibians, to lizards, to dinosaurs and pterosaurs, which I'm going to talk about today. And in these cases, typically we only have bones, their skeletons to work with. We typically can't know the colors or what color the feathers were of these animals or what kind of soft tissue they had. Now, there are exceptions to all of these. There are very rare cases where colors are preserved or feathers are preserved, or even some soft tissue, skin impressions are preserved. But this is not the norm by any means. For the most part, we only have the skeletons. And as we saw with Emily's presentation, so many examples of sexual dimorphism today are only present in these features, whether it's soft tissue crests or the colors of the feathers or what have you, which we don't have with the fossils. So to find sexual dimorphism in the fossil record, we need to have enough individuals to get what we call bimodal distribution. And so bimodal distribution, bi means two, and mode refers to these peaks. So if you plot your data, so this is just a hypothetical graph I threw up that doesn't actually represent anything, any real occurrence. But on the y-axis, we have the number of specimens. So these peaks we have a bunch of specimens that represent this condition and a bunch of specimens that represent this condition. And this condition here, I just wrote the length of crest. So you have a bunch of individuals that have a small crest size and a bunch of individuals that have a large crest size. And in this case, the peaks are even, which means you have about 50-50. And when you see a 50-50 split in some trait like that, it's likely to be a result of sexual selection. But to even get that bimodal distribution, you need a large sample size, which, like we said, is not common. You need well-preserved specimens, and those specimens often have to be three-dimensionally preserved, which means with things like birds or pterosaurs, which are very small and lightly built, they often get smushed like roadkill during the fossilization process. And so it's like you're looking at a piece of paper rather than a 3D bone, which can make things difficult because that often obscures detail that you definitely need. So when we do see differences between fossils, like between two fossil organisms, that doesn't necessarily mean that they were a boy and a girl, because these differences, they could be sexual dimorphism. It could be different species. They could be different ages. Maybe an animal was injured and that alters how the bone grows or appears to us. Or you could be looking at some just individual variation within a species. So there is a lot to consider. And there have been a lot of cases of proposed sexual dimorphism in fossil animals. that have been that have since been dismissed because we found out like, oh, did you consider, like, the original authors didn't consider that like these animals are different ages instead of a different sex or something like that. And as a result of all of these limitations of the fossil record, we will never know about the overwhelming majority of cases of sexual dimorphism in extinct animals. But sometimes in rare cases, we can tell. So first up with dinosaurs. So dinosaurs, many of them, not many of them, a lot of them had these very flashy crests on their heads and frills and spikes and so forth. And like Emily mentioned, with modern animals, with you might expect these things to be display structures, and they probably were. But you might also expect them to differ between males and females. You might think, oh, males might have bigger, flashier, bony crests, and females would have smaller. Now, is that the case? It doesn't seem it usually is. So first up, we'll talk about Allosaurus. We do not see sexual dimorphism in Allosaurus. But the reason I talk about it is because it is a very well represented dinosaur in the fossil record. So Allosaurus was a dinosaur that lived in the Jurassic period, and its fossils are found in Wyoming, Utah, and Colorado, but especially in Utah. Now, a lot of their fossils are found in the Cleveland Lloyd Quarry in Utah, which is a very small area, and it has tons of dinosaur fossils in this very constrained area. It's the densest accumulation of Jurassic dinosaurs anywhere in the world. And from this one quarry alone, there's like 46 Allosaurus specimens. Like, that's a crazy number of Allosaurs for this one area. And an obvious question is, what are they all doing there? Especially considering they outnumber the herbivores like 2 to 1 or 3 to 1. There are way more carnivores here than there are herbivores. And that is not the norm. Usually carnivores are very rare. So with this quarry, some people have hypothesized that it was a predator trap, kind of like the Livraea tar pits, where some big herbivores got stuck in the mud, and then their stinking corpses attracted predators to scavenge, and then they got caught in the mud, and that attracted more predators, and then they got caught in the mud, and so forth. That's not settled. I'm not convinced of that interpretation. I think what's more likely is that it was a flood deposit of some kind. So basically, a lot of these animals probably died of a drought or something, and then a large 1,000-year flood would have accumulated these bones into one area. Anyways, all that to say, my point here is that there are a lot of Allosaurs, nearly 50 specimens from this one quarry. And that is about as good of a sample size as you can hope for dinosaurs. But despite having so many specimens, we don't see a hint of bimodal distribution. We don't see a difference in size. We don't see a difference in the length of the skull. We don't see a difference in any crest or ornamentation on their heads. So there's no trace of sexual dimorphism in the skeletons of these animals. That doesn't mean, just to be clear, that doesn't mean they didn't have sexual dimorphism. That just means there is no skeletal differences. So it could have been differences in the color, or it might have had different colors of feathers. We don't know if this animal had feathers or not. It probably did. They might have had some kind of keratin overgrowth on their horns that wouldn't have fossilized. But if they did have it, it was not preserved in the bones themselves. Next up, a dinosaur that needs no introduction, Tyrannosaurus Rex. So several years ago, we found this leg bone of a T-Rex that we cut in half, or broke. I think we cut it in half. And we sliced it and found that there is this porous bone lining the inside of the leg bone. And the paleontologists in charge of this, in charge of the study, noticed that they compared it to the bones, or an occurrence that we see in modern birds, and that is called medullary bone. And medullary bone, we found, only occurs in when a female bird is like preparing to lay eggs. And so not only can we tell this was from a female T-Rex, this was from a female T-Rex that was pregnant. Now, obviously, if you haven't figured it out by now, this is not a reliable indicator of sexual dimorphism for a few reasons. First of all, we can't slice open every femur of a T-Rex we have. Second, females are not pregnant year-round, right? So this is just a chance occurrence that this female happened to be pregnant when she died. So this cannot be taken as an indicator of, or a reliable indicator for distinguishing males and females, because, not even within females, not all of them are pregnant at the same time. And as far as we can tell, there are no other indicators of sexual dimorphism in Tyrannosaurus. So again, just like Allosaurus and most other dinosaurs, we can't tell. Now, with Kentrosaurus was a relative of Stegosaurus. Only this guy lived in Tanzania instead of the United States. It's similar to Stegosaurus in that it has plates on the front half of its body, but then it changes into spikes in the back half, as well as big old spikes coming out of the shoulders. It's a pretty metal-looking dinosaur. But there is an analysis of the femurs, the leg bones of these animals, that and that study concluded that the males were bigger than the females because they saw two different size classes. We have that bimodal distribution we talked about. And it's likely that the males were larger than the females, like we see in many animals living today. Ceratopsians are an animal because of the great diversity we see in the frills and the horns. You might think, oh, maybe the males had bigger, fancier frills and horns than the females, but this does not seem to be the case. Now, one explanation for that would be sample size, maybe, because for a lot of these species, we only have 1 or 2 or 3 individuals, and that you can't conclude much at all based on that few specimens. However, we do have a lot of specimens of Triceratops. Those are these 3 here, different species of Triceratops. And in Triceratops, we have tons of individuals from Triceratops, dozens or even hundreds. And we do not see a trace of difference we don't get that bimodal distribution in Triceratops. And so that suggests that the females and males would have looked basically the same. Now, like Emily mentioned with Bighorn sheep, the males would have almost certainly competed against one another and used these horns to combat one another to fight for mates. But it's not like the males had bigger horns than the females or anything like that. Now, moving on to pterosaurs. Pterosaurs were flying reptiles that lived during the same time as dinosaurs, but were not dinosaurs themselves. Pterosaurs were not dinosaurs. I cannot emphasize that enough. But many pterosaurs, like Pteranodon here, the most famous one, had a variety of crests on their beaks and on top of their heads. And this is another thing that you might expect to see, at least in modern animals, you would expect to see some sexual dimorphism in. So similar to dinosaurs, we generally don't see a difference in crest shape in pterosaurs. We don't get a bimodal distribution in relation to crest shape. But it's very likely that in life, animals like Tupindactylus up here would have had a much more vibrant head than the female would have. Just like in modern birds, the females are probably more drab and the males were very showy, like Geosternbergi over here or Tropognathus here. Now there is an exception to this, when that is Pteranodon. So Pteranodon is probably the most famous pterosaur by far. But there is some research by Chris Bennett in 1992 where he found some bimodal distribution. So he found 2 peaks in his data for a number of different traits. So there's 2 peaks here. Notice how one peak is bigger than the other. That means there are more animals that have this trait than the rest do. And this trait here, don't read too much into this graph because I'm going to simplify it for you. So this graph is basically showing how big the finger bones are. So how big these animals were essentially. And you can see that there are a lot more smaller animals than there were bigger animals, about twice as many smaller individuals than larger. So you immediately have 2 size classes, and that is exactly what you want to look for to figure out sexual dimorphism. And with this bigger size class, Bennett also found that they're generally bigger and more robust, These bigger individuals also have larger, more prominent crests sticking off the back of their head, while the smaller size class has just a little nubbin off the back of the head. He also noticed that the smaller size class generally have wider hips than the larger size class. And all of this in conjunction makes a very strong case for sexual dimorphism. Specifically, the females were smaller. They had a smaller crest because, like we said, the males are usually bigger and showier. So they have to have this big crest to impress the ladies. And the females would have also had wider hips to make the passage of eggs easier. And we see that in a lot of animals today. Additionally, there are many more individuals of the smaller size class, the females, than the males, which again kind of makes sense. And we probably had a situation very similar to sea lions today, or elephant seals today, where the males kind of had a harem of females. And so we would have had kind of these beach king pteranodons that would have mated with multiple females. And so here's a bigger picture, a little more clear of the skulls of these animals. You can see they are very different. Males were much, much bigger and had a way more prominent crest off the back of their head. We see a similar thing with the crests in a pterosaur called Hemipterus. Hemipterus was discovered just a few years ago, or actually now I guess it was like 7 years ago, which is crazy because I remember when this thing was found. But we find a bunch of three-dimensionally preserved skulls, which for pterosaurs is rare because, as I mentioned earlier, these are very lightly built animals and their remains are easily destroyed. But not these ones. These ones were 3D preserved, and most of them had preserved crests. And with these individual skulls, we found two kind of different types. We found one that had a gentle crest going along the length of the head, a very subtle crest, while another type had a much more prominent crest that also ran the length of the head. And you probably noticed the pattern that these larger crests were probably the males, and this more subtle crest belonged to the females. And additionally, this find was really cool because we actually found eggs preserved with all of these adult individuals, which probably indicates that this was a breeding ground for them. And both the females and males went to these small locations to breed and lay eggs. So in review, there are very few known cases of sexual dimorphism in the fossil record. To clarify, this does not mean that extinct animals didn't have as much sexual dimorphism as we see today. That's kind of a silly conclusion. There's no reason to think that. However, because of the limitations of the fossil record, we don't have the skin or the feathers or anything like that that usually harbor sexual dimorphism in modern species. That we have a loss of information. And not only do we not have the anatomical information, but we have a very small sample size. Specimens are often fragmentary and poorly preserved. And in addition to that, the results of a lot of these studies suggesting sexual dimorphism are subject to controversy. So with pterosaurs, I know, and dinosaurs, in many, many cases, one paper would come out that says, oh, we think we see males and females here. And another study will come out that says, oh, well, did you consider this? Did you consider that these specimens are actually different species? Did you consider that these specimens are just like juveniles and not fully grown? And so proving sexual dimorphism in paleontology is very tricky, and most cases will remain unknown. And with that, I'm going to pass things over to Daniel, where we're going to see.
Okay, are we all good? Thumbs up? Yeah, okay, cool.
Yep.
So how's it going, everybody? Wildman Dan here. It's great to be with you guys again, talking about sexual dimorphism, as my great classmates have already talked about in great depth. We got to look at it from the dinosaur perspective or paleontology, as well as in a variety of different species, such as mammals, birds, reptiles, and even fish. We went into the marine section of it. I'm going to show you guys a species of rattlesnakes that is one of my personal favorite. It's called Crotalus lepidus, or also known as the mottled rock rattlesnake. Just a beautiful species. I got this girl from southern Texas, but these guys are usually primarily can be found in the Southwest. of the United States, as well as into Mexico. They are a venomous species of viper. They're part of the rattlesnake family, which means that they do have a rattle on the tip of their tail. And what they're going to do is they're going to shake that rattle, which is made out of keratin, same stuff that's on your fingernail, and it's going to make a sound. And that sound is going to warn us that we're getting a little too close. And what do we do when we get too close to a rattlesnake? We take 2 steps back, Jack. I just want you guys to always remember that. This snake has primarily a hemotoxic venom, which means that it's actually attacking the red blood cells, but it is known to carry a large amount of neurotoxins, which attack the nervous system, which is really scary to think about. I don't know about you, but I don't want to stop breathing or my heart to stop in like a matter of seconds. So stay away from the snake. It's good for you. It's good for the snake. But let me show you guys this beautiful animal and tell you a little bit about how this animal, at least some of the species, show sexual dimorphism. It's pretty awesome. So, snake, and are you guys ready for this beautiful creature? There he is. So here we go. This is Microtalus lepidus, also known as the rock rattlesnake, the banded rock rattlesnake. A beautiful male. The way you can tell this guy is a male is going to be from the actual tail itself. Now, the tail technically is classified from the cloacal vent all the way down to the tip of the tail, which is where the rattle will actually begin. So for those who do not know, reptiles have what are called cloacas, also the same thing that birds do, where the reproductive organs as well as the excretory organs are all located in the exact same place. So basically, they use the bathroom and reproduce from the same exact area. That's called the cloaca. And so we look at the tail from the cloaca, where the cloaca starts, all the way to the tip of the tail. Now, mainly, males will have a really long tail, and it usually is a little bit skinnier compared to a female's when we're talking about snakes specifically. Females will usually have a short and stubby tail. And with that short and stubby tail, that's how we usually can distinguish basically between male and female. Now, sometimes with snakes, you can also tell by the size of the head. Sometimes males' head size will be larger than females, even though the majority of them don't use it to actually hold down a female in any way, shape, or form. Although I do believe when we're talking about king snakes, those guys actually do. They'll actually clamp onto the female to make sure she doesn't get away. But with these guys, it's really unique, and I think it's a species in New Mexico specifically, where I'm from, that the males are green and the females are pink. So that's how you can tell right away whether or not you're looking at a female or a male. Just like we saw with the peacocks, how the peacocks are usually really colorful, the boys are, but the females are really dull and not colorful. Same thing with these mottled rock rattlesnakes. Some of these species, the males are really vibrant and green, while the females are also vibrant, but they're just a completely different color, pink. Now, I don't know too much in regards to why this is. It doesn't look like it plays any role with them deciding a mate that we know of so far, but maybe with further studies and a little bit more research, we'll figure out exactly why there's such different colors. Sometimes it takes just a little bit of time to learn something and figure it out. But just like most pit vipers, these guys do have heat sensing pits right there at the tip of the nose, or not at the tip of the nose, but just below the actual eye. They're a much smaller species of snake, but really just one of my absolute favorite snakes. Like the speckled rattlesnake, depending on what kind of colored rock they are, they usually match that color. So they can be anywhere from this really light gray to a blue to a purple, red. They can have speckling all over themselves, or like the clobberi, which is a really close cousin of those. That is the banded rock rattlesnake. They won't have any speckling, but they'll just have really beautiful band lines that go across. And those guys also show a little bit of sexual dimorphism, where you'll see that difference in coloring from that green and that pink. But just a beautiful species of snake that just loves to do what it does best, which is hunt and look for food and try to stay away from us as much as possible so that we don't end up stepping on them. But in the reptile world, there is sexual dimorphism also, even with snakes and lots of different vipers. Sometimes you'll see difference in colors on the actual face of a male versus a female. Some tree vipers have this. And sometimes it's just size in general. because females usually carry a lot of eggs, they're usually a lot girthier and thicker than males will. So I almost got tagged. Thanks, guys. It was a great time. We hope to see you guys next week.